So imagine cutting your diffusion model's inference compute in half, speeding up your training by an order of magnitude, and, well, actually generating significantly better images.
Which sounds completely made up, right?
It really does, but you get all of that by just adding some numbers together and recycling a mathematical feature you are already computing anyway. Today on AI Paper Slop, we are jumping straight into the paper Improved Baselines with Representation Autoencoders.
Authored by researchers from Adobe Research, ANU, and NYU.
Right. And here is your zero intro summary. This paper introduces RAE v2, which is an architecture that hits a state-of-the-art GFID of 1.06 on ImageNet 256 in just 80 epochs.
Which is incredibly fast.
Yeah, it's a 10 times faster convergence over the original Representation Autoencoders. And it pulls this off through 3 brilliant training-free architectural tweaks. First, swapping out single-layer encoder outputs for a generalized multi-layer sum.
That's a big one.
Second, proving empirically that RAE and REPA, which is representation alignment, are actually complementary mechanisms, not redundant ones. And third, reformulating the REPA head to output X prediction.
And that final trick is what gives you internal guidance completely for free.
Exactly, effectively killing the need for expensive classifier-free guidance or secondary auto-guidance models.
It's just a phenomenal piece of engineering. I mean, this is one of those dense, highly practical papers that basically rewrites the underlying recipe for how you train diffusion transformers using frozen vision encoders.
Totally. So welcome to AI Paper Slop, where we cut through the noise and get straight to the signal of the latest ML research. Our mission for today's deep dive is to unpack the mechanics of this paper.
Right, because we want to understand exactly how these 3 tweaks squeeze Pareto optimal reconstruction and generation out of off-the-shelf vision encoders.
Like Dino v3L, for instance. But more importantly, we want to figure out why this specific workflow might completely change how you approach training your next diffusion transformer. So to really appreciate what RAV2 accomplishes, I think we need to look at the baseline flaw of the original RAEs.
Yeah, we have to start there.
Because originally, representation autoencoders were fundamentally lagging behind traditional variational autoencoders, or VAEs, when it came to just simple image reconstruction. Why was that happening?
Well, to understand the flaw, we first have to appreciate the premise of an RAE, which, I mean, it's beautiful in theory.
Right.
Usually when you build a diffusion model, you have to train this highly specialized VAE from scratch just to compress your images into a latent space. And that takes a massive amount of compute.
It's a huge bottleneck.
Exactly. So the RAE approach basically says skip that. You already have these massive, robust, pre-trained vision encoders out in the world. Just freeze one, pass your image through it, and use its internal representations as your latents.
Which completely unifies your tokenization for both understanding tasks and generation tasks.
Right, but as you mentioned, the original implementations fell short on reconstruction quality. The images would come out blurry or, structurally warped. And the authors of this paper identified the exact culprit.
Which is what?
Prior RAEs were only using the final, deepest layer of that pre-trained vision encoder.
Which honestly makes intuitive sense as to why it would fail at reconstructing fine detail.
Oh, absolutely.
Because by the time an image is processed all the way through a deep vision transformer down to the very last layer, the model has abstracted away almost all the low-level geometry and texture.
Right. It just knows the high-level semantic concept.
Yeah, it knows, oh, this is a golden retriever in a park. It doesn't care about the precise pixel-level edge of the dog's fur or, the exact shape of a leaf in the background.
Exactly.
If I can use an analogy here, trying to reconstruct an image using only that final layer is like trying to understand the intricate layout of a massive, complex novel by only reading the final chapter.
That is a perfect way to visualize it.
Right. RAEV1 gave you the plot spoiler, but none of the world building.
Yeah, the final chapter tells you who committed the crime, but it strips away all the environmental descriptions you'd need if you were asked to physically reconstruct the crime scene.
So RAEV2 introduces what they call a generalized, training-free formulation. Instead of just taking layer L, the final layer, they utilize the last K layers of the encoder.
Right. They aggregate those layers to capture the rich, diverse abstractions that exist across multiple depths of the network.
So you get the high-level semantics from the end and the low-level textures from a few layers back.
Precisely.
But let me push back on that for a second, just from an engineering and memory standpoint. If you have a massive foundation model like Dino v3L, and you decide to take, let's say, the last 7 layers,
right,
how do you aggregate those features without completely blowing up your parameter count? Because if your feature dimension is D and you just concatenate 7 of those layers together, suddenly your latent dimension is 7 times D.
And that's a huge problem.
Yeah. The self-attention mechanism in your diffusion transformer scales quadratically. It is going to absolutely choke on that kind of dimension explosion.
Well, the authors fully anticipated that bottleneck. So to preserve the original latent shape, which is your sequence length n, by your dimension d, without adding any newly learned parameters, they tested 2 distinct aggregation schemes.
Okay, what was the first one?
The first approach was multi-layer random projection, or MLR. This is where you do exactly what you just described. You concatenate the last k layers along the channel dimension, but then you project it back down to the original dimension using a fixed random matrix.
Wait, random projection, like multiplying that massive concatenated vector by a fixed, completely random matrix?
Yep, initialized just once at the start.
But if you do that, aren't you just mashing the data through a random filter and destroying the information?
You would certainly assume it scrambles the data, but it actually relies on a fascinating mathematical property of high-dimensional spaces.
Oh, the Johnson-Linden-Strauss lemma.
Exactly. According to the lemma, you can project high-dimensional data into a lower-dimensional subspace using a random matrix, and it will actually preserve the pairwise distances between the data points in expectation.
That's wild. So the underlying geometry survives.
It does. But the second method they tested was even simpler, and quite frankly, a little hard to believe at first glance. They called it multi-layer sum, or MLS.
Which is just...
You literally just take the features from the last A layers and do an element-wise addition. You just add them together.
Just adding them element-wise. That sounds like, I don't know, mixing 7 different intricate paint colors together and expecting a masterpiece. Shouldn't that just give you a muddy brown?
It really sounds like it should.
Doesn't the signal from layer 20 completely overwrite the signal from layer 24?
It seems like it should cause catastrophic interference, right? But again, we have to remember we are operating in incredibly high-dimensional space.
Okay, so what does that mean in practice?
Well, in a space with hundreds or thousands of dimensions, random vectors, or vectors representing different abstract features, tend to be nearly orthogonal to one another.
Ah, I see. Because they are practically sitting at right angles in that massive mathematical space, you can superimpose them on top of each other via simple addition without the signals crashing into one another.
Exactly. And the empirical results from the paper were absolutely definitive. Both MLR and MLS tied on stage 1 reconstruction metrics, which is your RFID.
Right.
But MLS consistently and heavily dominated on stage 2 generation performance, measured by GFID.
Let's actually ground those metrics for a second. So FID, or first at inception distance, measures how indistinguishable your generated images are from real ones, accounting for both quality and diversity. Lower is always better.
Right. The lower, the better.
And looking at the specific numbers from the paper at k = 7, the multilayer sum method hit a GFID of 2.637, but the random projection method only hit 3.118.
Yeah.
That is a massive performance gap just from choosing to sum the layers instead of projecting them.
It's a striking difference. And it proves that a tight summary of those last few chapters gives the diffusion model exactly what it needs.
It's so elegant.
The simple addition retains the low-level texture from the earlier layers and the semantic richness of the later layers. And best of all, it keeps the latent footprint completely identical to the original baseline. You get a massively upgraded map of your image, and you pay 0 extra memory overhead to store it.
Okay, so the multilayer sum trick gives us this beautifully rich, textured, latent space map. But having a highly detailed map is completely useless if the diffusion model doesn't know how to navigate it spatially.
Very true.
If the tokens aren't talking to each other correctly, you end up with a dog's eye attached to its tail. So how do we force the intermediate layers of the model to respect that spatial geometry?
Which brings us to the second core insight of the paper regarding REPA. And honestly, this is the one that completely upends the prevailing wisdom in the field.
Representation alignment, or REPA. It's been a popular technique lately. The basic idea is that you take a pre-trained representation and you distill it into the intermediate layers of your diffusion model.
Right. You are essentially giving the middle of the network a target to aim for to help guide its spatial structure as it denoises.
But the prevailing assumption has always been that if you are already using an RAE, meaning your starting latent space is already defined by a frozen Dino v3 model, using REPA to align the intermediate layers to that exact same Dino v3 model seems completely redundant.
It feels incredibly redundant.
It feels like brewing a pot of coffee and then pouring it through a second identical coffee filter. You already extracted the flavor profile at the input stage. Why are you forcing the intermediate layers to align to the very thing they were conditioned on? Shouldn't it just act like a wasteful, computationally expensive skip connection?
That was the exact intuition almost everyone in the field shared. It felt redundant. But the authors of this paper decided to actually test that assumption.
And what did they find?
They ran a massive, large-scale analysis across 27 different vision encoders, and they uncovered an incredible paradox. REC and REPA actually operate through highly complementary mechanisms.
Wait, even though they're using the exact same feature vector?
Yes, they're not doing the same job at all.
I'm going to need you to break that down. How can injecting the exact same mathematical signal do two completely different things, just depending on where you apply it in the architecture?
It fundamentally comes down to what specific part of that dense signal, the diffusion model, actually leverages at different stages of its processing.
Okay, go on.
When the researchers analyzed models using REPA alone, without the RAE latents, they found that generation performance correlated incredibly strongly with something called local distance similarity, or LDS.
LDS.
LDS is a metric that measures the spatial structure of the features. So it looks at how different localized tokens pay attention to each other. The correlation between RVA success and high LDS was negative 0.89.
Wow, that's high.
But here is the wild part. REPA's performance was actually anti-correlated with linear probing, which is the metric used to measure global semantic information.
Let me see if I have this right. REPA is basically acting as an architectural spatial regularizer. It forces the intermediate diffusion features to respect the raw geometry of the image making through the edges line up and the proportions make sense, but it doesn't really care about the high-level semantic labels.
Exactly.
It ensures the walls of the building are perfectly straight, but it doesn't care if it's building a house or a spaceship.
That is a brilliant way to phrase it. It cares about structure, not semantics. Now, flip the experiment. When they analyzed RAE on its own, without REPA, the exact opposite phenomenon occurred.
No, really?
Yeah. RAE generation performance relies almost entirely on global semantics. It correlated with linear probing at negative 0.81, but it barely showed any correlation with the spatial LDS metric at all.
That's fascinating.
RAE gives you a semantically rich, highly conceptual, latent space at the input, but it struggles to enforce strict spatial consistency as the diffusion process unfolds.
So when you combine them, it's just a perfect marriage. The RAE handles the what is this object global semantics at the input level, and the REPA head steps in to handle the where are the parts of this object located spatial structure at the intermediate layers.
Precisely. And neither metric alone can predict success when you combine the two techniques.
Right.
But the authors found that if you take the mathematical average of an encoder's linear probing score and its LDS score, that combined average achieves the highest overall correlation with generation quality.
Which completely explains their findings on encoder selection.
Exactly.
If you need a model that scores incredibly high on both global semantics and localized spatial structure for this combination to work, that is exactly why a massive, robust encoder like Dino v3L absolutely crushes the benchmarks.
It does. Dino v3L excels at both tasks simultaneously. It is essentially the perfect dual-threat foundation model for this architecture.
It really is. And embracing that paradox, accepting that injecting the same signal twice actually targets two completely orthogonal mechanisms, sets up the foundation for their third and arguably most impactful architectural hack.
Yes, the free guidance hack.
This is the section of the paper that will make any ML engineer who is currently dealing with severe inference bottlenecks sit up and pay close attention.
Oh, without a doubt.
Because once you have these structurally sound latents from the multi-layer sum, and you have optimal alignment by combining RAE and REPA, you still have to deal with the notorious guidance problem during inference. And original RAEs were fundamentally incompatible with the industry standard, which is classifier-free guidance, or CFG.
They were. To get CFG to work, you normally have to do a conditional forward pass using your text prompt, and then an unconditional forward pass using an empty prompt.
Right.
You take the difference between those two outputs, multiply it by a guidance scale, and use that vector to push the model heavily toward your specific prompt. But with original RAEs, executing that empty, unconditional pass completely wrecked the mathematical distribution of the latents. The images would just collapse.
Yeah. So to fix it, developers had to rely on a workaround called auto-guidance.
Right, which is brutal.
Auto-guidance is an absolute nightmare for compute complexity. You literally have to train an entirely separate, weaker diffusion model from scratch just to act as the baseline to contrast against your main strong model. It essentially doubles your training pipeline overhead.
It's a massive tax.
CFG doubles your number of function evaluations, your NFEs at inference time because of that second pass. Auto-guidance doubles your model count at training time. So if we aren't doing a second pass and we aren't training a secondary weak model, where is RAEv2 getting its guidance from? How does it get it for free?
Well, the authors had a massive realization. They already have a weaker model built directly into the architecture.
Oh, it's the REPA head.
It's the REPA head.
Okay, let's unpack this carefully. The RAPA head is attached to the early intermediate layers of the diffusion transformer. It is doing its processing before the signal has reached the full depth of the network.
Exactly the right framing. The RAPA head produces an output based on incomplete early layer computation.
Right.
It is, by definition, a weaker, blurrier prediction than the full model's final output. But to use that weak prediction for guidance, they had to ensure both outputs lived in the exact same mathematical space. This is where the concept of X-prediction reparameterization comes in.
I want to make sure I understand the mechanism here. Usually standard flow matching or diffusion models predict velocity, the V prediction. They are trying to predict the trajectory of the noise removal. But X prediction means the model is trying to predict the actual pristine target data directly from the current noisy step, correct?
Yes. And if you reformulate the full model's output to give you X prediction, and you force the REPA head to also output X prediction, now both parts of the network are speaking the exact same language. They're both generating a guess of what the final image should look like.
But how does the actual guidance calculation happen? With CFG, we subtract the unconditional pass from the conditional pass. What are we subtracting here to get that guidance vector?
You are subtracting the weak prediction from the strong prediction. Think of it like this. The REPA head gives you an early, structurally sound but incomplete guess of the final image. The deep, full model gives you a highly detailed, semantically rich guess. By using a deep, supervised network approach detailed in Equation 3 of the paper, you subtract that weak REPA guess from the strong, full model guess.
Okay, that makes sense.
The difference between them creates a mathematical vector that points precisely in the direction of more fine detail and better global alignment. You multiply that vector by your guidance scale, add it back into the process, and you push the image quality significantly higher.
And the absolute genius of this is that the REPA head is already being computed during the standard forward pass of the network anyway.
Exactly.
You don't need a second unconditional pass. You don't need to load a second model into memory. You just grab that intermediate output on its way through, contrast it with the final output at the end, and boom, you have your guidance vector. You're effectively halving the NFEs compared to CFG.
You cut the inference compute in half. And the ablation tables in the paper prove that this isn't just a sneaky computational shortcut. It actually yields dramatically superior image quality. The internal REPA guidance achieves a GFID of 1.06.
Which completely beats the auto-guidance baseline at 1.14 and absolutely obliterates traditional CFG, which was stuck at 1.49. You are getting better generation quality for half the inference compute without having to train a secondary model. In machine learning, that is the literal definition of a free lunch.
It truly is. It brilliantly turns the REPA head from just being a spatial regularizer during training into a critical, self-contained inference engine for guidance.
So let's zoom out and look at the whole package. We now have better latents through the multi-layer sum trick. We have optimal feature alignment by embracing the paradox of combining RAE and REPA. And we have free internal guidance via X prediction.
Right, the trifecta.
But let's talk about what this actually translates to for your day-to-day engineering workflows. How do the training speeds and generalizations actually hold up in practice when you deploy this?
Well, to measure the practical impact, the authors adopted a really interesting metric inspired by the Speedrun community in the language modeling domain.
Oh, like modded NetOct.
Exactly.
Yeah.
If you look at projects like that, the cultural obsession right now isn't just about hitting a higher benchmark. It's about how incredibly fast and cheap you can hit a known baseline. To capture this, they introduced a metric called EPFID at K.
Which stands for epochs to reach an unguided GFID less than or equal to K. I absolutely love this cultural shift in the ML community.
It's so healthy.
It stops researchers from burning thousands of dollars of compute chasing a 0.01 improvement at Epoch 2000, and refocuses everyone on raw training efficiency. How fast can you get this model to a usable state?
Well, the speedrun numbers here are staggering. REV2 drops the EPFID at 2 metric from 177 epochs in the original RAE baseline all the way down to an astonishing 35 epochs.
177 epochs down to 35. That is a massive reduction in GPU hours and training costs.
It really is. And if you look at the newly proposed representation Frischate distance metric, or FDR6, which scores sample fidelity across 6 entirely different feature spaces to prevent models from just hacking one specific metric, RAEV2 hits a 2.17 in just 80 epochs.
Wow.
It completely crushes the previous best architecture, which scored a 3.26 and required 800 epochs of training to achieve it.
A 10x speed up to hit state of the art. But I have to ask the tough question here. Is this just an ImageNet party trick? We've seen a lot of architectures look absolutely incredible on class conditional ImageNet generation, but they completely fall apart the second you ask them to handle complex, temporally compounding tasks.
Right, the real-world test.
Does this robust latent space actually generalize to something brutal, like predicting the future in video?
That is the ultimate stress test for any generative architecture, and the authors knew it. So they applied RAE2 to navigation world models, or NWM, using the Recon dataset.
Okay, so what does that entail?
This isn't just generating a single static picture of a dog. This task requires the model to perform autoregressive rollouts, generating video at 4 frames per second for up to 16 seconds based on robotic navigation data.
And autoregressive video generation is so punishing because errors compound exponentially. If your spatial structure is even slightly degraded or blurry at frame 1, the model conditions frame 2 on that mistake.
Yeah, the snowballs.
By the time you reach frame 64, the image is usually melted into completely incoherent static.
That temporal flickering is the bane of world models. But this is where everything comes full circle. Remember the very first trick we discussed, the generalized RAE using the multi-layer sum.
Yeah.
By pulling in the features from the earlier encoder layers, that K-layer trick, the latent space retains strict mathematical low-level textures and geometry.
Oh, I see it now. Because we didn't throw away those early layers, the model has a physical anchor. It's not trying to hallucinate the geometry of the room from pure floating semantic concepts. It has the raw structural data embedded in the latent space to carry over consistently from frame to frame.
Exactly. The geometry doesn't drift.
That is incredible.
The geometry stays locked, and the results are stark. The Frischate video distance, or FVD, for the original RAE baseline on this video task was an abysmal 32.01. With the RAEV2 NWM setup, that number plummets down to 105.61.
That's a huge drop.
The temporal flickering is largely eliminated, the structural integrity holds across the 16-second rollout, and again, it converges in a fraction of the training steps.
It's incredible to see how all three of these architectural insights stack seamlessly on top of each other and translate flawlessly from static ImageNet generation to autoregressive video. Let's briefly recap the journey we just took.
Let's do it.
We saw how simply abandoning the single-layer paradigm and summing multi-layer features gives us Pareto optimal latents without blowing up the parameter count.
Right.
We saw how embracing the apparent paradox of using RAE and REPA together actually targets two distinct complementary mechanisms, global semantics and spatial structure.
Right.
And finally, we saw how reformulating the REPA head to output X prediction turns it into a built-in free guidance mechanism, effectively having inference compute while achieving state-of-the-art FID scores in a fraction of the time.
It really demonstrates how much untapped potential still exists in the mathematical representations of frozen vision encoders. We don't always need to blindly throw more compute at a problem or, train new specialized components from scratch.
Yeah.
Sometimes we just need to learn how to intelligently route, aggregate, and reparameterize the signals we already have.
Which brings up a final paradigm-shifting question about where the entire field is heading. I'll let you take this one to close us out.
It is something for you to seriously consider the next time you boot up a long training run. If off-the-shelf, completely frozen vision foundation models like Dino v3 already contain all the necessary low-level geometry and high-level semantics required to achieve state-of-the-art generation without any specialized fine-tuning, are we nearing the actual death of the dedicated VAE?
Wow.
In a few years, will the entire concept of spending thousands of GPU hours training a specialized tokenizer for your diffusion model seem just as archaic and outdated as handcrafting feature extractors before the deep learning boom? Because the math in this paper strongly suggests that the future is already frozen.